Out beyond the lantern glow of our own galaxy, so far that distance itself begins to feel like a dream. Astronomers stumbled on something the sky's rulebook never planned for. More than 13 billion light-years away, they found islands of stars so heavy, so neatly built, that they look older than the cosmos that cradles them. Imagine ancient cities, fully lit, standing in the dark when the universe was supposed to be only an infant. These galaxies hold as many suns as the Milky Way, yet they shimmer into view at a time when, by every schedule we trusted, there should have been little more than mist and promise. Tonight we'll drift through those impossibilities, discoveries that make the foundations of our science creak, meeting galaxies that seem to outrun physics, and peering at ideas bold enough to double the age of everything we think we know. Settle in. Breathe slowly. Let the room grow quiet. If you like wandering the deep night like this, float along with Space Historian. Tap subscribe and leave a gentle like so the journey continues, then sink back into the story. The James Webb Space Telescope did more than give us sharper eyes. It nudged reality's edges and asked if they're where we thought. Close your eyes and hear the instruments power on, the first images whispering down to Earth. July 11th, 2022, a date that rethreads the tapestry. Scientists were braced for first steps and baby pictures, smudges of newborn galaxies, clumpy and unsure. Instead, giants stepped onto the stage. At a quiet desk, Dr. Erica Nelson watched a tiny red fleck on her monitor, a dot so small it could have been a trick of the screen. It should have been a faint, struggling smear, the kind of early galaxy still learning to light its first stars. But the software pulled the distance and mass, and the numbers made her sit up so quickly her coffee rippled. Distance, roughly 13.1 billion light-years. Mass, on the order of 100 billion stars. That lone red speck held a star count in the Milky Way's league, yet it lived when the universe was only about 700 million years old. It was like walking into a nursery and finding among the cots and the warm hush of lullabies a fully grown oak with rings upon rings in its trunk. Our pictures of how galaxies grow say they need time, enormous breaths of it. After the beginning, stars must ignite. Then they must live and die in those hot, noble endings that scatter carbon, oxygen, and heavier elements into space. Only with those ingredients can the next generation rise, and the next layering structure, until grand spirals and ellipticals take shape. It should take billions of years, a careful, patient recycling of light and dust. But this galaxy glowed as if it had skipped the queue entirely. The light looked old. The structure looked sophisticated. The fingerprints of heavy elements, atoms that should not have been minted yet, were there in its spectrum, like seasoned spices in a kitchen that shouldn't own them. The discovery didn't nick the timeline of cosmic evolution. It sliced through it. If the cosmos was a mere 700 million years old at that snapshot, where did this galaxy borrow all that time? The ripples turned to waves. Either the way we think galaxies assemble needed a rewrite so sweeping it would cover the sky, or the universe itself was older than our best clocks declared. In the halls where cosmologists compare notes and sharpen arguments, a quiet sentence began to pass from person to person, uncomfortable and magnetic. What if the Big Bang story needs mending? Dr. Nelson and her colleagues had walked into what would soon be named, with a mix of awe and unease, the impossible early galaxy problem. Within months, more objects like it appeared. Each new point of light deepened the riddle, decorum giving way to wonder and the kind of skepticism that, when honest, is only curiosity in armor. And all of it started with a little red dot that refused to be little in any other way. Think of the universe running on an ancient schedule. First fog, then clarity, then stars, then the slow architecture of galaxies. That schedule felt inviolable. In the beginning, the cosmos was a hot, dense blend. No atoms, only a blinding broth. For roughly 400,000 years, nothing could settle. When the radiation thinned and the fog cooled, hydrogen and helium finally clasped into atoms and drifted through the dark. Gravity took a long breath, some 100 million years, before it could tug those gases into the first star-forming clouds. The first stars were titans, short-lived, ferocious, and generous in death. Their explosions stitched the heavier elements into the fabric of space. With those elements on hand, the next generation could begin and begin again until galaxies like ours could lift their faces to the night. This is construction, floor by floor, foundation, framework, walls, the patient finishing touches. The cosmos, we thought, built the same way, but the galaxies in Webb's mirror looked like skyscrapers raised before the blueprints were dry. Heavy elements that shouldn't be printed yet, stars that shouldn't be born yet, shapes that shouldn't have lined up so soon. It's as if someone completed a cathedral between breakfast and dusk. The arithmetic faltered. If the universe began about 13.8 billion years ago, and we're seeing these objects as they were 13.1 billion years in the past, only 700 million years remained for all that grandeur to happen. Our current physics says such mass and complexity should require at least 2 billion years of cosmic labor. Something, then, is off. Our models of galaxy formation might be missing essential gears, or the universe's age might be misread, leaving more time in the margins than we penciled. Or, least comfortable of all, the story of the Big Bang itself might need a revision that keeps us up at night in the best way. The cosmic clock is ticking. Its hands point somewhere unexpected. Among the thousands of galaxies Webb sketched, a peculiar breed stole the eye. Astronomers christened them little red dots, tiny rubies on the black velvet, objects that older telescopes simply couldn't coax into view. They would become the smoking gun in this sprawling mystery. Unlike most galaxies that sing in many colours, these dots shone fiercely in the infrared while dwindling to near nothing in other bands. Their redness hinted at two possibilities, each dramatic, either hordes of weathered, ancient-feeling stars, or the fierce glow of a central black hole swallowing matter with bright, messy appetite. The first of these dots, when its light was teased apart and weighed, carried a mass of roughly 100 billion suns, comparable to the Milky Way. Yet it lived when the universe was a mere 5% of its present age, a grown adult standing among newborns. The colour told its own tale. In a young universe, we expect galaxies to skew blue, heated by hot, massive stars burning fuel rapidly. Redness usually means maturity, stellar populations that have been humming along for a very long time. But these dots felt both young and old, youthful in cosmic timestamp, elderly in their starlight's character. Snow in high summer. As Webb's images multiplied, so did the red dots. They were not a handful of freaks, they were a population. Some estimates ran 100 times more abundant than standard Big Bang models would predict. The community divided itself into thoughtful camps. Some argued that early galaxy formation must simply be far more efficient. The universe, under pressure and density we've not adequately captured, might manufacture stars at a pace that shames our simulations. Others suggested the dots could be mirages of a sort, galaxies whose central black holes blaze like beacons, their glare washing out the surrounding starlight and tricking our measurements. But a growing circle whispered the deeper possibility that the dots were not illusions, but messages, signals that the framework itself needs work. In the heart of any galaxy, The alchemy is simple. Clouds of gas and dust cool and crumple, fragments condense, and stars, after millions of years, switch on. This is the rhythm we know. Slow, resistant, self-limited. But the massive early galaxies Webb turned up seem to have held their breath and sprinted. To shape a galaxy with 100 billion stars in only 700 million years requires star formation turned up to a setting our physics doesn't recognize. Even in perfect conditions, calm gas, deep gravity wells, little turbulence, our best models say a galaxy can convert only about 10% of its gas into stars before feedback blows the rest away. Young, massive stars flood their neighborhood with radiation and wind, heating gas to millions of degrees. That hot gas expands, pushes, and quells further star birth. It's a thermostat, a cosmic safety valve. For those early giants to build so much so fast, they would have had to defeat the built-in brakes. Maybe the early universe was denser, the thinking goes. The pressure of the environment so great that hot gas couldn't escape and cooling was far quicker. Maybe dark matter made deeper, sharper wells, corralling star-forming material more tightly and holding it against those winds. In computer experiments, researchers attempted to bottle such conditions, but the results misbehaved. Either not enough stars formed, or too many, with galaxies shredding themselves under their own energy. And yet the sky insists. The galaxies are there, proof that the universe somehow found a route to star formation that looks like a time lapse. Billions of years of work compressed into a few hundred million. The implications wander beyond astronomy. If our rules for how matter cools, clumps and shines are incomplete, we need new ones. And if they're complete but misapplied, we need to learn where the early cosmos bent them without breaking. Now, sink further into the quiet and picture the centers of these great early structures. In the core of almost every large galaxy, a monster waits. Supermassive black holes, carrying millions or billions of solar masses, curving space so drastically that even light finds it hard to leave. In the early universe, these titans are even stranger than their host galaxies. The red dots do not only stack impossible numbers of stars, they appear to harbour black holes that shouldn't be there yet. Their light carries telltale signatures. Gas spirals inward and heats to incandescent temperatures, releasing torrents of energy. The glare can outshine the galaxy itself. We call the brightest examples quasars, but a black hole grows by eating, and eating takes time. There's a limit, polite in a way, on how quickly matter can fall in. As the infalling gas heats and shines, its radiation pushes back, fighting gravity. This balance creates a speed limit called the Eddington limit, the fastest sustainable feeding rate. Even if a black hole dined constantly at that maximum pace, it would still need hundreds of millions of years to swell from the seed left by a dead star into a supermassive presence. The objects Webb uncovered seem to have accomplished this growth in a fraction of the available time. Some of these central engines, if we trust the numbers written into their light, would have needed to eat 5 times faster than nature's own speed limit, and to keep that pace for as long as they'd been alive. It's the astronomical version of claiming someone gained 1,000 pounds on one small meal a day. The math refuses to budge. The physics as we teach it simply doesn't allow it. Yet the first generation of black holes seems to have ignored the house rules and grown anyway. And then the riddle turns back to the beginning. Where did such black holes come from at all? In the usual tale, the first colossal stars flare, live briefly, and collapse, leaving behind the seeds. Modest black holes that, with patience and plenty of fuel, can swell across the ages. But in the earliest dawn, time is the precious currency. Stars must first form, then burn, then die. Only after all that can a black hole even inherit the stage. That sequence alone nearly spends the available minutes, leaving too little for the feasting and the growth we now see written across the sky. So new sketches of the story have been drawn. One suggests that some black holes were born not from star death at all, but from the direct, quiet implosion of gargantuan, metal-poor gas clouds. No supernova fireworks, just the universe folding a pocket of itself into darkness. Another whispers about primordial black holes, ancient objects seeded by early universe fluctuations before there were stars to speak of, speckling the cosmos as ready-made cores that later galaxies could gather around. Each idea moves a piece on the board, offering more time or bigger starting seeds. But whichever doorway we choose, a deeper strangeness waits just beyond the threshold. Because what if some of those early heavyweight galaxies were not heavyweights at all, but master illusionists performing with light? Imagine a spotlight so bright you can't count the candles in the room. That is what a ravenous black hole can be. Matter spirals into an accretion disk. Friction squeezes it to a fever, and it blazes, so bright it can drown the chorus of starlight around it. A core like that can make an ordinary host look extravagant. When we weigh a galaxy by the light in our nets, we might be weighing the beacon more than the city. This mirage notion promised a graceful exit from the crisis. If many little red dots are not truly behemoths, but modest galaxies with overactive hearts, then the cosmos didn't need to assemble skyscrapers overnight. The limits we trust could stand. The timelines could breathe again. Yet illusions, when you study them long enough, confess their boundaries. Even if the stage light blinds us, the bulb itself still needs a fixture. The black hole's glare requires a black hole to exist, and a big one. So the puzzle doesn't evaporate, it migrates. Instead of asking, how did we make so many stars so fast, we're left asking, how did we make these massive black holes so soon? And when some of those red dots are examined with the finest combs we own, we don't just see the signature of hot feeding cores. We also see the hushed collective glow of huge stellar crowds. In those cases, the galaxy is not merely bright, it is genuinely vast. The mirage can explain a portion of the sky's tricks, but not the whole act. So astronomers have been sorting the cast. Which giants are true giants, and which are rooms lit by blinding lanterns? As that work goes on, another possibility steps forward, one that strolls in from an older corridor of ideas, dusting off its sleeves. In 1929, while Edwin Hubble was measuring the heavens and finding that distant galaxies wore a red tint, evidence, he argued, that space itself was stretching and carrying them away, a Swiss astronomer, Fritz Zwicky, offered a different lens. What if the galaxies weren't moving apart? What if the light was simply tiring? In his picture, photons lose energy as they travel the deep, their wavelength stretching with the effort, reddening not because the source flees, but because the journey itself is costly. Call it tired light, a static universe wearing a red veil from the miles under its feet. For a long time, tired light sat at the edge of the stage, asked to explain too many things it couldn't. It struggled with why faraway galaxies appear smaller than a truly static universe would allow, and it had little to say about the cool, uniform microwave afterglow we see wrapped around everything, the cosmic background that, in the standard view, whispers of a hot, dense beginning. And so the idea faded. A footnote in the lecture, but Webb's red dots, like errant comets, have a way of stirring old dust. If the universe were not expanding after all, then the far-off galaxies we gaze upon wouldn't be newborns caught in the act. They'd be as old as they look, genuinely ancient. That would hand them the time our current clock denies, the centuries needed to form stars leisurely, to build structure without breaking the speed limits of physics. From this revival has emerged a bolder hybrid, tired light, revamped with care, paired with the suggestion that the so-called constants of nature might not be perfectly constant. In this blended world, some calculations point to a universe roughly 26.7 billion years old, a cosmos almost twice the age we now recite. Within such an antique realm, even the most distant islands of stars could have been busy for eons before their light began its pilgrimage to us. This is more than a clever patch. It is a challenge to the floorboards beneath modern cosmology. If the cosmic red shift is not the drumbeat of expansion, but the fatigue of long travel, then our sense of time, how we place beginnings and middles, must move. And if the anchor points of physics wink and sway even slightly, then the early universe may have played by a different rulebook. Under those rules, stars might have gathered more swiftly. Black holes might have grown with alarming ease. Galaxies might have assembled their bones while today's laws were still soft clay. Variable constants are not a brand new dream. Some versions of quantum gravity quietly allow for such shifts, as if the universe tunes itself like an instrument across scales and epochs. But turning that notion into a working map is a delicate business. Adjust too much and you ruin the nearby scenery. The background radiation, the ratios of hydrogen and helium forged in the first minutes, the delicate dance of structure formation. The knobs must be set just so, like finding the exact station on an old radio by ear, static fading only at a sliver of the dial. In one telling of this hybrid model, the early cosmos is allowed a different set of dials, slightly altered strength for gravity, a subtly different speed of light, just enough to quicken starbirth and fatten black holes without throwing off the other constellations of data. Tired light then handles the redshift without expansion, freeing the distant galaxies to be honestly old. It is an elegant construction on paper, and elegance is often a good sign. But elegance isn't proof. Critics, patient and necessary, point out the landmines. Vary the constants, and you must still reproduce the microwave background's exquisite patterning. You must still match the observed ratios of primordial elements. You must still explain why the changes took precisely the form that lets everything else look as it does now. Proponents reply that we already carry mysteries in our standard kit: dark matter and dark energy, invisible scaffolds and gentle pushes whose natures remain veiled. So perhaps allowing the constants to breathe is no more radical than believing in unseen mass and pressure. The conversation tightens, circles, and opens again, like lungs filling and emptying in a sleeping room. If you're drifting with this tale, let it wash over you. The questions are not loud, they hum. Are the laws of physics truly carved in stone, the same in every corner and hour? Or do they evolve as the universe does, co-authoring the story as it goes? While philosophers of measurement and theorists of gravity turn those puzzles over in their hands, the galaxies Webb found continue to hang in the dark, serene, and unapologetic. When faced with such stubborn light, astronomers reach for their most versatile forge, the computer simulation, where whole universes can be cast and tested, where the ingredients can be stirred and the stove turned up and the results compared to the sky. If the models can't birth early giants, then perhaps the giants are ghosts. If the models can, then nature has simply found a path we hadn't traced yet. The first attempts gave the same verdict again and again. Using the physics we trust and the recipes we've refined, cooling, gravity, feedback, and the rest, the simulated early cosmos produced baby galaxies as expected, clumpy, small and shy. None resembled the rubies we were seeing in the real remote night. The code said no. The telescope said yes, but code can learn. Researchers added detail, sharpened their treatments of turbulence and radiation, tested unusual initial conditions and new sequences of mergers, and a different route began to appear, like a short trail through the trees you only notice at dusk. What if the early universe had brief fits of ferocity, star-making frenzies that flared and faded, compressing ages of growth into moments? Cosmic brainstorming sessions, if you like, when two young galaxies collided and interwove, funneling their gas toward the center where gravity presses hardest. During such episodes, the gas becomes a tide, pouring inward. Pressures climb, clouds cool quickly, stars ignite in rolling waves. The thermostat that normally slows the process can be temporarily outmatched by sheer density and inflow. For spans short in cosmic time but meaningful in outcome, a galaxy could convert an astonishing fraction of its gas into stars. The Knight's factory runs near perfectly, throwing almost nothing away. In pictures like these, you can resolve two truths at once. First, the bursts create dazzling, compact beacons, systems so bright and red that they look ancient and heavy. Second, the underlying mass need not always be as titanic as the glow implies. If a galaxy is caught mid-frenzy, its light can mislead the scale in our hands. Seen from afar, amid the haze of early dust and the stretch of the spectrum, a starburst can masquerade as a colossus, which loops us back to where the mirage and the reality meet. Some of Webb's red jewels might be modest in bone, but radiant in breath, their brightness a temporary crown. Others truly carry the mass, their splendor earned the slow way by assembling deep wells of stars. And for each class, the physics is likely different in nuance and emphasis. Gas richness, merger history, the character of local dark matter, the timing of feedback. Sorting them requires patience and better spectra, more time on the instruments, and a willingness to let multiple answers share the same sky. If these starburst windows were common enough, and if the early universe was crowded enough to feed them, then the simulations suggest a surprising outcome. For brief, frantic intervals, a galaxy could look like a heavyweight even if, on the scales, its true stellar mass was much smaller. This bridge between what we see and what we expect felt, for a moment, sturdy underfoot. Picture the early cosmos as a crowded, restless city at rush hour. Lanes merging, engines revving, side streets funneling traffic into glowing hubs. In that crush of motion, galaxies didn't grow politely. They slammed together, their gas reservoirs channeled inward, igniting short, furious epochs of starbirth. To a distant eye, that frenzy looks like impossible adulthood, a face lined with the marks of time, even if the body underneath is younger than it seems. The models added another accomplice to the illusion: dust. Fresh, hot stars forge dust quickly, and that dust does a quiet magic trick. It drinks the bluer light and re-releases the energy in the infrared, the very wavelengths Webb is tuned to savor. Through that filter, a compact, vigorous system can masquerade as old and vast, red, heavy-seeming, a veteran of ages it hasn't actually lived. In the ledger of explanations, this simulation salvation hinted that the universe might not break its own rules at all. It might simply play the game at harder difficulty. Same physics, fiercer settings. Slip now from that busy city to a whisper that fills all rooms. Between radio stations, between the static and the songs, there's a faint warmth that doesn't belong to any single source. That is the afterglow of the beginning, the cosmic microwave background, the soft, even murmur released when the universe was only about 380,000 years old, back when electrons and protons first settled into atoms and the fog thinned enough for light to travel freely. Spread across the sky, it's almost perfectly uniform, yet spangled with tiny temperature flecks, a pattern that fits the expanding universe story with unsettling precision. Those flecks are the seeds, minute density ripples, that gravity later coaxed into the bristling web of galaxies and clusters. Ripples on a pond, widened by time. For tired light, this glow is a hard question. In an expanding cosmos, the background cools naturally as space stretches, preserving the exact black body curve we measure with exquisite instruments. In a static universe, that same smooth, perfect spectrum must come from something else, and from something else that behaves just right. Advocates have tried on ideas. Perhaps the microwave fog is the sum of all starlight ever made, pushed to longer wavelengths by energy loss along its travels. Perhaps it's a bath produced by interactions between photons and a cosmic medium that drains their vigor, whisper by whisper, until they hum in microwaves. Recent attempts to write down a tired light cosmos that yields the same gentle curve show it isn't logically impossible. But the bookkeeping is intricate, the mechanisms unfamiliar, the knobs adjusted to fine settings. The standard picture wins on simplicity. The alternatives live by careful tuning. Yet the background tells more than one story. Its near-perfect sameness asks ancient questions. How did the early universe become so even, so smooth, that regions on opposite sides of the sky, too far apart to have ever spoken, if light is the speed limit, share the same temperature? Why do the tiny differences that do exist carry precisely the statistical fingerprints we see? These puzzles point beyond expansion versus static. They glance at the deep rules of causality and space-time, at whatever processes flattened and ironed the primal fire into such an orderly quilt. As teams continue to map that faint glow with finer resolution, the microwave background remains a crown witness. It doesn't shout. It simply sits there, precise and patient, asking every new cosmology to fit its curve and its speckled texture without smudging the rest of the sky. Meanwhile, another invisible actor holds more than 4/5 of the universe's matter in its grip: dark matter. It does not shine or block or glow, it tugs. It bends light passing near. It keeps stars swirling in galaxies from flinging themselves away. It seeds the wells into which ordinary gas falls to make suns. In our current script, dark matter supplies the scaffolding. Galaxies are the walls and windows built atop. Webb's early heavyweights press on that idea. To cradle a giant galaxy so soon, you need a giant dark matter halo first, an unseen basin to collect and hold the baryonic stuff. But the best simulations of the early universe produce few such basins at those redshifts, and those they do produce are smaller than the ones these observations seem to require. The timeline cramps again. So, the suggestions. Perhaps dark matter was more tightly concentrated in the beginning than we model. Perhaps it has a shy self-interaction, a way of nudging itself that speeds the assembly of structure. Each variant would shift a cornerstone of how we think the cosmic web formed, and each must pass the gauntlet of other evidence. Galaxy rotations, lensing arcs, the delicate proportions of the background's mottling. Change the recipe here, and the loaf must still rise the same way everywhere else. The tired light angle reframes it. If the universe is far older than we think, if the furthest galaxies are seen at their true, grey-templed age, then dark matter halos have had ages to fatten. There's no need to sprint. They walked. In a 26 billion-year-old cosmos, even the most remote lights would have had long seasons to accrete mass and deepen their wells. The youth would be a mirage of interpretation, not of nature. But even then, the inventory must close. The same dark matter that sculpts rotation curves and lenses clusters must exist and behave in ways that match a library of measurements. solve one tension, keep the others intact. Some of the most vivid evidence for how the early universe lived doesn't arrive as a quiet map, but as a snapshot of chaos. The most distant galaxy merger yet seen. 13 billion light-years away. Light leaving when the first sunrise of stars was newly pink. Two large galaxies are caught mid-embrace, their tidal arms flung out in long, glittering streams. Mergers are ballets of gravity and violence, never about head-on crashes of stars. Space is too roomy for that, but about orbits warped and gas herded. Over hundreds of millions of years, the choreography draws the cores together. The central black holes spiral inward like skaters clasping hands, and in the last instant their union rings space with gravitational waves. This particular dance raises the familiar timing ache. Both partners already look mature. Billions of stars, discernible structure, engines awake in their hearts. For them to exist and find each other when the universe was roughly 500 million years old, if our clocks are right, asks for a pace we've never seen otherwise. Add to that the signs of lunatic star formation lighting their overlap regions. Newborn stars kindled at rates that make today's galaxies look idle. Maybe the early universe held more of these meetings. Maybe gravity had more raw material to work with. Maybe collisions weren't the exception but the weather. Run the collision forward on a computer, and the merged remnant grows into something with Milky Way scale. Our galaxy took nearly the whole age of the cosmos, by our standard, to reach its present mass through a steady diet of minor mergers and long quiet feasts. How then does the young universe serve the same meal so quickly? Again, the central engines may help explain it. Both galaxies flash the signatures of actively feeding black holes. These cores can regulate star formation, both spurring and suppressing it, shaping the timing of a galaxy's life. In the early days, they may have been decisive, not ornamental. Each new observation of that ancient crash scene reads like a memo from a wilder time. More density, more interactions, more fuel. The serenity we associate with the night sky is a local late luxury. Back then, the cosmos was lively, nearly boisterous. But astronomy is not only images and stories, it is, at its heart, spectra, the splitting of light to read its code. When the crisis of early giants burst into focus, everyone knew the deciding votes would be cast by spectroscopy. Pull the light into its rainbow and measure the lines. There you find the elements present, the temperatures reached, the speeds at which gas approaches or recedes. If the early heavyweights were phantoms of glare or bookkeeping errors in distance, the spectra would betray the trick. The verdict wasn't a single page, it was a sheaf. Some objects that photographs crowned as massive turned out, under the prism, to be quasars, central black holes so incandescent that they overwhelmed their homes. In those cases, the lighthouse outshone the shoreline, and the mass we thought we saw evaporated in proper accounting. But many others held up under the sharper lens. Their spectra showed the blended, steady glow of large, diverse stellar populations, the fingerprints of complex chemistry, the hallmarks of mature systems already layered in structure. These were not mislabels or nearby interlopers wearing the wrong red shift. They were what the first look suggested: massive galaxies, young in cosmic time, old in character. One surprise cut especially deep. Those mature fingerprints include heavy elements, carbon, oxygen, iron, born in stellar cores and supernovae and spread by stellar winds. In our familiar era, it takes a procession of generations to enrich a galaxy. Stars form, live, die, and refill the pantry for the next batch. Billions of years pass before the mix reaches the recipes we see today. Yet these early systems already had those ingredients in meaningful amounts as if a whole cycle of birth, death, rebirth had been compressed into a few 100 million years. The chemical clocks ticked faster than we knew clocks could tick. Spectroscopy also hardened the distances. The positions of spectral lines, shifted redward by known amounts, pinned these galaxies to the far horizon. Their light truly left when the cosmos was newly awake. They are not closer masqueraders in dusty masks. That firmness shut off an easy escape hatch. Perhaps most revealing of all, the spectra sketched a landscape, not a monoculture. Some galaxies blaze with ongoing star formation, thick with nurseries. Others already look quenched, their factories dimmed. Even that early, the ecosystem was varied, the tempos out of sync. One size does not fit the dawn. Taken together, these lines and curves and quiet numbers forced a single, unavoidable message through the noise. The spectroscopic evidence left astronomers with an undeniable conclusion. The ledger finally tipped. The young cosmos had, against every expectation, assembled fully grown-looking galaxies in a blink. Long before Webb's mirror set those rubies in the dark, astronomers already knew the early universe underwent a feverish rite of passage. Reionization. Around 1 billion years after the beginning, the first lights rose in numbers, great enough to scour the fog of neutral hydrogen, turning an opaque cosmos into the clear, transparent vastness we peer through today. The giants that Webb unveiled weren't just statistical outliers, they were forges and furnaces at the centre of that transformation. Their crowded nurseries of newborn stars and their ravenous central black holes poured out hard radiation, ionizing great bubbles of space until those bubbles overlapped and the curtain lifted. In the old diagrams, reionization was a slow thaw. Countless small galaxies, sparks more than bonfires, would chip away at the mist for hundreds of millions of years. But plant a few early titans into that same dawn and the weather changes. Reionization begins to look abrupt, jagged, more like brush fires racing along dry grass than dew drying under the sun. Condense the timeline and everything else compresses with it. The first stars form earlier. The black holes fatten sooner. Clusters and filaments take shape with less idle time between steps. Even the grand calendars on which we place cosmic milestones need new margins. Clues to this faster drumbeat come from the oldest light we can still touch, the polarization etched into the cosmic microwave background. Read carefully, those delicate patterns suggest that reionization may have started earlier and proceeded more briskly than standard schedules predict. It is a second voice, independent of Webb's pictures, murmuring the same theme. The early universe was not a quiet nursery, but a lively marketplace. Reionization also helps explain the redness that gives the little red dots their name. Bathed in intense radiation, the intergalactic medium around those galaxies heats and agitates. Blue light scatters, ricocheting away. Redder wavelengths slip through more easily. To our infrared-tuned eyes, the galaxies wear an older look, a deeper hue. Some of what we read as age is in part the colour of the water they're swimming in. As teams weave together direct observations and the steadily improving experiments in silicon, the simulations that let us test whole histories, the reionization epoch emerges as a hinge, a decisive turn where the impossible-looking becomes merely unexpected. The lesson is not just about when the fog lifted, but about how quickly the universe can renovate itself when conditions are extreme. And still, as evidence accumulated, a bolder thought found enough footing to be voiced without a whisper. Maybe the pressure point wasn't in our models of star-making or merger rates, but in the foundation we set those models upon. The Big Bang framework, with its long list of triumphs, might still be missing a page. Something about time's texture, or space's appetite, or the rules that ran hottest when the cosmos was young. Alternative cosmologies have lingered like side paths on a hiking map, marked, rarely taken. Webb gave some of them fresher ink. In cyclic universes, expansion and contraction follow one another like seasons without end. The present outward sweep would be one beat in an eternal rhythm, with structure layered over structure from cycles beyond counting. Give the cosmos all the time it wants, and too fast loses its bite. Another family of ideas opens the door to extra dimensions, an architecture broader than the four rooms we know. In such spaces, energy and matter can flow in ways that accelerate assembly, feeding galaxies with channels that don't exist in our simpler blueprint. Elsewhere, the steady-state concept, once the Big Bang's chief rival, steps back into view in modern dress, attempting to keep the universe forever roughly as it is, while explaining the background glow and the patterns of redshift with mechanisms like tired light and other energy loss processes. Perhaps most audacious are the models that allow the knobs of physics to turn over time. Let gravity's strength or the speed of light differ in the early epochs by the smallest amounts, and the bottlenecks of star formation and black hole growth might widen just enough. The appeal is obvious. The cost is high. Each alternative must account for everything the standard picture nails: the background's perfect spectrum, the primordial element ratios, the sculpting of the cosmic web. The crisis that sparked these explorations isn't a free pass. It is a stern invitation to completeness. While those philosophies rise and reshape and are pared back by data, Webb's infrared gaze has been telling a humbler, tactile story, one written in dust and gas, the bricks and mortar of galaxies. With its heat-seeking vision, Webb doesn't just sketch silhouettes, it measures what the nurseries are made of. Dust, microscopic but mighty, drinks starlight and re-emits it as a warm murmur in the infrared, changing how gas cools, how clouds collapse, how stars ignite. In a universe so young, dust should have been scarce, made mostly in the throats of dying stars and in the flowerings of supernovae. Yet those early giants glimmer with it, as if several stellar generations had already lived and given their ashes back to space. That wealth of dust whispers speed, a fast-breathing cycle of birth and death, compressed into centuries at cosmic scale. And the gas tells its own secrets. High-resolution spectra reveal torrents of inflow, rivers of hydrogen and helium streaming toward galactic centers, feeding both the star factories and the central engines. The rates exceed anything we measure nearby today, as if the early universe played with heavier dice. Simulations of those flows, in a denser, warmer background, show how cooling can be turbocharged, how pressure can help gravity, how a cloud can be persuaded to collapse quickly rather than linger on the brink. The fingerprints of mergers are there too, written in the way gas moves, disturbed, asymmetrical, off-kilter. Many of the Dawn's galaxies bear the scars and benefits of recent unions. In all of it, the portrait emerges of a cosmos not just youthful, but different in kind. Thicker, quicker, more chemically adventurous than we dared draw a decade ago. The tiniest grains and the most featureless gases, when counted carefully, become historians in their own right, narrating how simplicity sprinted toward complexity. And then there's the universe's own magnifying glass. Gravitational lensing. Mass bends light. Enough mass turns the cosmos into optics. A distant galaxy's glow, skirting a fat cluster's gravity, can be stretched, brightened, doubled, even ringed into a halo. For astronomers, lensing is a natural telescope, one that lets us see further and fainter than our mirrors alone can manage. Some of the loveliest early finds arrived amplified by these cosmic lenses. But the lens that helps can also trick. Magnification can make a modest system look regal. Without careful modelling of the intervening mass, we can mistake the lens handiwork for the source's true heft. Untangling the two requires patient reconstructions of the lensing cluster, estimates of the amplification, and the humility to adjust a galaxy's measured size, brightness, and mass back down once the lens is subtracted. In return, lensing sometimes gives us a gift no ordinary observation can. Multiple images of the same background galaxy, each taking a slightly different path around the lens. With those echoes, we can probe structure, star formation knots, and chemistry from different angles, stitching together a fuller portrait than any single view allows. In the last few years, lensing has carried us closer to the horizon of the observable universe than we had hoped to tread so soon. Faint smudges turned into identifiable shapes, spectra teased from whispers, distances pushed back step by careful step, each aided by gravity's quiet optics. And with each step, we nudge the edge of the map outward, pushing back the frontiers of the observable universe. Through these lens-boosted windows, we meet galaxies born only a few 100 million years after the first light, infants by any calendar we kept, yet already singing with many voices. Gravitational lensing becomes the universe's own instrument, the curvature of space itself, bending and brightening distant beacons so we can study what would otherwise be lost in the dark. As our models of lensing grow more exact, accounting for every cluster, subhalo, and sliver of mass along the line of sight, these natural telescopes will keep pulling the horizon nearer. But lensing also reminds us of a deeper truth. In astronomy, observation and interpretation are dance partners. What we see is never just what is, it's what is, braided with how the cosmos carries light to us. Every galaxy is a choir made of countless voices. Each star contributes its tone to the sum, and hidden inside that blended music is a biography of birth and change. To unbraid it, astronomers use stellar population synthesis, a craft equal parts physics and archaeology. The method asks, if I mix these kinds of stars in these proportions, at these ages and metallicities, under these dust veils, would the light look like the light I observe? It is detective work built from spectra and colours. How bright in the blue, how warm in the red, where the absorption lines sit, how wide they are, how much the continuum curves. From those clues we infer how many stars there are, which types dominate, and when the great bursts of star formation began and tapered. Applied to Webb's early heavyweights, that technique doesn't tell a simple tale. It hands us a tapestry. Some systems bear the signature of wild, short-lived starbursts, as if a match were struck in a wind, flaring hot, then subsiding. Others look layered and paced, their light implying a more gradual assembly. The most arresting detail is the presence of red giants already shining in those dawn-era galaxies. Red giants are stars in late chapters, cores spent of hydrogen, envelopes swollen. If they are there, then star formation must have started hundreds of millions of years before the moment we're observing, enough time for smaller suns to age into those swollen forms. In such a young universe that reads like a margin note, the timeline wasn't supposed to allow. The chemistry corroborates the rush. When we measure the relative amounts of oxygen, iron, and other heavy elements, the yields of stellar cores and supernovae, we find surprisingly high abundances. That means nucleosynthesis had already run several laps. Stars formed, cooked heavier elements, exploded or shed their layers, and seeded the gas for the next generation. Heavy elements pervade the spectra like seasoning in a dish that hasn't had time to simmer, unless somehow the stove was set much higher than we knew it could go. Another clue sits inside the infrared initial mass function, the recipe that says how many small stars, and how many massive ones a galaxy forms at a given time. In the nearby universe, low-mass stars are plentiful and massive stars rare. But several early systems look top-heavy, skewed toward massive stars. Those giants blaze hot and die young, dumping heavy elements into space at a furious rate. That would help explain rapid chemical enrichment and the swift appearance of dust. A top-heavy IMF is a lever. Pull it, and you hasten both the brightening of galaxies and the birth of the conditions that make more stars possible. To be faithful, the synthesis models themselves must change clothes for the early universe. The background was denser, the radiation fields harsher, cooling channels different, dust compositions not yet like the ones in today's spirals. Each of those environmental differences shapes how stars ignite, live, and end. As teams fold those conditions into their codes, a picture emerges of a cosmos that forged stars under rules that rhyme with ours but do not scan in the same meter. Piece by piece, Webb turned out not just a set of surprises but a pattern. Anomalies that could be waved away alone became a chorus when sung together. The accumulation reached a tipping point. The early galaxy problem grew into a systematic challenge. What began as a few red dots grew into a re-examination of our assumptions about how cosmic time is apportioned and how structure takes shape. That turn is not only astronomical, it is philosophical. The tale of science is not a tablet of fixed truth. It is a journal written in pencil. Webb's discoveries are a reminder that our best models are bridges, not bedrock, and that bridges are rebuilt when the river shifts. Healthy skepticism, stern with the data, generous with ideas, drives progress. It is no failing to ask if the frame itself needs a new joint. It is the practice. Explanations now jostle in the light. One camp reaches for modified physics within the standard expansion, star formation more efficient than we'd thought in dense, hot environments, black holes growing by channels we haven't fully modelled, cooling and turbulence working under extreme conditions to speed collapse. Another camp searches for time itself, proposing cosmologies that stretch the clock, cyclic universes with long winters and long springs, tired light-style mechanisms that alter how we read distance, models with varying constants that widen bottlenecks in the earliest epochs. Across conferences and preprints, the conversation moves fast. Talks open with Webb's rubies and close with equations that try to square them with everything else we know. The background spectrum, element ratios from primordial nucleosynthesis, the lattice of the large-scale structure, the arcs of gravitational lenses. This shift is also about how we practice astronomy in the age of instruments like Webb. New capabilities don't just add pages, they change genres. Infrared sensitivity of this precision doesn't give sharper versions of familiar scenes. It reveals actors who were never on stage before. With each dataset, we learn how much of our prior ignorance was simply a function of sight. As more observations arrive, from Webb, from ground-based spectrographs, from future radio arrays that will map the neutral hydrogen fog itself, the pace of this shift will quicken. Some results will push us further from the standard map, others will rescue the central lines with new footpaths traced through extreme physics. Either way, the process is the same. Observe, model, fail, improve, repeat, until picture and prediction shake hands. The broader lesson? Science is not a monument to certainty. It's a lighthouse built anew every night. The impossible early galaxies force us to acknowledge the shoreline has moved. Whether we are about to redraw the coastline entirely or just adjust the bays and headlands, we cannot pretend the old map was complete. The evidence points toward a universe that, in its youth, ran its rules differently, or at least pushed them to edges we haven't frequented. Here are the signposts. Galaxies massive and mature when they shouldn't be. Black holes swollen fast enough to dare our limits. Chemical enrichment accomplished with bewildering speed. These are not one-offs. They are monuments, scattered through the young cosmos to how much we have left to learn. And Webb is still only beginning its watch. With every deeper stare, every tighter spectrum, we push further back, seeing not only more, but clearer. Surprises will multiply. Some will magnify the tension, some will ease it. Each will refine our questions. If this kind of stargazing calms your mind and lights it in equal measure, drift with Space Historian. Tap subscribe and leave a gentle, like so this journey can continue in the background of your nights without disturbing the hush. Whether these findings ultimately crown alternative cosmologies or simply edit the Big Bang's early chapters is an open book. What is clear is that the universe resists our tidy categories. It refuses to be the classroom exercise we once imagined. It is subtle, emphatic, and at times gleefully disobedient to our expectations. With every century of study, the unknown remains larger than the known. That is not defeat, it is invitation. So we keep going. We let the data be thorny. We allow our theories to be brave but testable. We welcome the dissonance because harmony earned is sweeter than harmony assumed. The next results will arrive, and with them, paths we did not know to look for. The story of these early giants remains unfinished, the ink still wet on the page. Soon enough, new instruments will ask sharper questions of the same light. New surveys will catch galaxies at even earlier hours of dawn. New simulations will uncover regimes where the impossible becomes ordinary under different starting conditions. Perhaps the crisis will mature into revolution. Perhaps it will settle into refinement. Either way, the view has already shifted. Our home is stranger, more intricate, more alive with possibilities than the models we carried into this decade. What other secrets is Webb sharpening its gaze to reveal? Subscribe to Space Historian to float along as we listen for the next whispers from the dark. Add a like so more night wanderers can find the path and keep close the wonder that there are still questions vast enough to cradle us to sleep. The universe has become a place where the impossible does not stay impossible for long, and our work will never be finished, only deepened. The cosmos is calling, and we are finally ready to answer.